A sudden push strikes from behind. The upper body pitches forward. Weight shifts toward the toes, and the center of mass begins moving beyond the area supported by the feet. A fall now appears unavoidable, but before the human eye can fully recognize what has happened, sensors have already detected the disturbance. A computer estimates the direction of the fall, calculates the forces required at multiple joints, and decides whether the robot should remain in place, swing its arms, or take another step. All of this happens within a fraction of a second. So how can a machine weighing dozens of kilograms balance on two relatively small feet and recover from an unexpected impact? The answer is a continuous feedback loop connecting sensation, prediction, and movement. And sometimes, the only way for the robot to avoid falling is to deliberately step away from where it was standing. Balance is not simply the ability to keep the upper body vertical. Every object has a center of mass, a point representing how its total mass is distributed. When the vertical projection of that center remains inside the area supported by the points touching the ground, the body can usually remain standing. For a robot supported by 2 feet, this area is called the support polygon. It roughly covers the space beneath and between both feet. But a push causes the center of mass to accelerate. If its momentum carries it beyond the support polygon, gravity begins rotating the body toward the ground. Position alone is therefore not enough. The robot must also know how quickly its center of mass is moving and where it will be a few moments later. It must react to a fall before that fall has fully developed. The first warning comes from the inertial measurement unit mounted inside the torso. Its gyroscopes measure how quickly the body is rotating, while its accelerometers detect changes in motion along several axes. When the humanoid balance robot is pushed, this compact module immediately senses abnormal acceleration and body tilt. At the same time, every joint position encoder reports the angle of its joint. Together, these encoders reveal how far the hips, knees, and ankles are bending and allow the computer to reconstruct the shape of the body. Beneath each pressure-sensing robotic foot, changes in load reveal whether weight is moving toward the heel, the toes, or one edge of the sole. The 6-axis ankle force torque sensor measures how the ground is pushing and twisting against the leg. Even before a foot lifts away from the floor, this combination of signals can reveal that the robot is beginning to fall. None of these sensors is perfect. Accelerometers can confuse body motion with gravity. Gyroscopes slowly drift. Foot sensors vibrate during impact, and joint measurements contain tiny delays. Raw readings therefore cannot be sent directly to the motors. The real-time balance control computer combines them through a process called state estimation. It compares the motion of the torso, the configuration of the humanoid internal skeletal frame, the forces at the ankles, and the pressure beneath the feet. From this information, it estimates body orientation, joint velocity, contact state, center of mass position, and momentum. This calculation may be repeated hundreds or even thousands of times every second. A delay of only a few dozen milliseconds could make the controller respond to a body position that no longer exists. Once the current state has been estimated, the robot must choose the smallest response capable of stopping the fall. For a weak disturbance, the first defense is the ankle strategy. The high torque joint actuators at the ankles change the force applied through the heels and toes. This shifts the center of pressure across the floor. The resulting ground reaction force creates a turning effect that guides the torso back toward its stable position. Humans use a similar response when standing on a train that begins to accelerate. The movement is fast, subtle, and energy efficient. But the center of pressure cannot move beyond the physical edges of the feet. Once it reaches that limit, the ankles have no additional leverage available. A stronger push activates the hip strategy. The robot rapidly rotates its upper body around the hips, moving the pelvis, shoulders, and arms to redistribute angular momentum. If the torso is falling forward, the hips may shift backward while the shoulders and arms move in the opposite direction. The arms do not need to touch the ground to influence balance. Accelerating an arm in one direction creates a reaction through the rest of the body. This is why a robot may suddenly swing its arms after being pushed. The motion can look clumsy, but it may be precisely calculated. Even so, the hips and arms can only redirect a limited amount of momentum. If the center of mass is moving outward too quickly, they merely delay the fall. At that moment, the robot must abandon its original support polygon and create a new one. It takes a step. The real-time balance control computer estimates a capture point, the location where a foot should land so the robot can stop its current motion. A step that is too short leaves the center of mass moving beyond the new support area. A step that is too long may be impossible to complete in time and could create another unstable movement. The controller must choose which leg to move, lift the foot without striking the other leg, and generate a safe path toward the target. Meanwhile, the supporting leg carries the robot's weight and continues correcting the torso. The moment the moving foot touches the floor, pressure and force sensors confirm contact. Load is redistributed between the legs, and the actuators begin absorbing the remaining momentum. If one step cannot stop the motion, the capture point is calculated again. The robot may take a second or third step, with every landing, creating a new support area. What appears to be uncontrolled stumbling can actually be a sequence of recovery plans, each one updated using the latest sensor data. The destination is not fixed in advance. It changes as the body moves, as the feet contact the floor, and as the available friction becomes clearer. The robot is continuously asking the same question: where must the next foot land so the rest of the body can be caught? This reveals something surprising about walking itself. Walking is not a perfectly stable condition. To move forward, the robot intentionally sends its center of mass beyond the support of the current foot. The body begins to fall, and the other leg moves forward to catch it. The cycle then repeats. Walking is a controlled sequence of falls and recoveries. The same principles that allow a robot to resist a push are already active during every step. The difference is that normal walking follows an expected plan, while an unexpected impact forces the system to rewrite that plan while the body is still moving. Modern robots often use predictive control to manage this process. Instead of correcting only the error that exists now, the controller calculates several possible future motions. It predicts how different joint forces, body movements, and foot placements could affect the robot over the next few moments. It then selects a response that preserves balance without exceeding the speed, torque, or movement limits of the joints. This prediction is repeated again as new measurements arrive. The robot never completes one permanent plan. It continuously replaces an aging prediction with a more accurate one. On a flat laboratory floor, the process can appear remarkably reliable. An external push test pendulum applies a controlled impact. An instrumented force plate measures the reaction beneath the feet, and high-speed motion capture cameras record the result. But the real world introduces a more difficult problem. The ground itself may not be trustworthy. On a low-friction test surface, sufficient motor torque may still cause the foot to slide. Loose gravel can move under load. Soft sand can sink, changing the height and angle of the support point. An uneven terrain course may offer only small areas where a foot can land securely. The humanoid vision sensor head helps identify obstacles, surface angles, and possible landing positions before each step. But vision can only predict what a surface might do. Force and pressure sensors must confirm what actually happens after contact. If the ground shifts or collapses, the previous plan becomes invalid. The controller must estimate the new position of the foot, recalculate the support polygon, and redirect the body before the disturbance grows. This is why a robot that survives a powerful push on a rigid floor can still struggle with a small stone, a wet patch, or an unexpectedly soft surface. No algorithm can completely escape physical limits. Actuators can produce only a finite amount of torque. Joints have restricted ranges of motion. A foot requires sufficient friction, and a stepping leg needs enough time to reach its target. If an impact creates more momentum than the machine can redirect or absorb, recovery becomes impossible even when the calculations are correct. Delays also accumulate. Sensors need time to measure, processors need time to estimate, and motors need time to generate force. Each delay may last only milliseconds, but a falling body continues moving during every one of them. When the humanoid balance robot survives a push, no single component deserves all the credit. The inertial measurement unit detects body motion. Joint position encoders track the configuration of the limbs. The 6-axis ankle force torque sensors and pressure sensing robotic feet reveal how the ground is supporting the machine. The real-time balance control computer combines those signals, predicts the developing fall, and chooses between ankle correction, hip rotation, or a new step. The result is a loop that never stops. Sense, estimate, predict, act, and measure again. And the most important lesson is that balance does not always mean remaining still. When motion has already escaped the limits of the feet, the robot must accept the fall for a moment, then place another foot in exactly the right location to catch itself.
Returning the system to perfect equilibrium.